I welcome you to another video on quantum computing. In this video, we will learn about the order finding algorithm. Few videos ago, we have learned about Shor's prime factorization algorithm, which is said to be a major breakthrough in quantum computing. However, Shor's prime factorization algorithm is a classical algorithm, except it calls a subroutine of order finding. So you can say that in this video we will learn about the quantum part of Shor's prime factorization algorithm. Let's start with the problem definition. Given positive integers alpha and capital N with GCD of alpha and capital N equals to 1, our goal is to find the smallest positive integer are member of multiplicative group on mod n such that alpha raised to power r is congruent to 1 in mod n. So that's our problem definition for the order finding algorithm. Let's do an example to make our concept clear. So in this example, my n is equals to 21, my alpha is equals to 2, and I have to find the smallest possible integer r such that alpha raised to power r is congruent to 1 in mod 21. My alpha is 2, so I can write instead of alpha 2 here. So because we have not yet learned the order finding algorithm, so I will take different values of r and try to find r using a brute force method. So let's try r is equals to 1. My equation will become 2 raised to power 1, which is equals to 2 in mod 21. So that is not my order. Now I try r is equals to 2. My equation will become 2 raised to power 2 is congruent to 4 in mod 21. That means 2 cannot be order. Now I try r is equals to 3. 2 raised to power 3 is congruent to 8 in mod 21. So 3 is not my order. I try r is equals to 4. 2 raised to power 4 is equals to 16 in mod 21. And so 4 cannot be my order. Now I try r is equals to 5. 2 raised to power 5 is equals to 32 is congruent to 11 in mod 21. So r is equals to 5 cannot be my order also. Now I try r is equals to 6. 2 raised to power 6 is equals to 64 which is congruent to 1 in mod 21. So that means 6 is my order for this example. So my R for this example is equals to 6. And also notice that this is a valid example because GCD of 21 and 2 is equals to 1. That means 21 and 2 has no common factors. Let's clear this part of the board. How to solve the order finding algorithm? We can solve order finding algorithm by employing phase estimation algorithm. In fact, order finding is polynomial time reducible to phase estimation algorithm. What it meant is that we can take phase estimation algorithm as a black box. We will not change its circuit or anything. We can only manipulate its inputs and outputs, and by manipulating phase estimation inputs and outputs, we can realize the order finding algorithm. To that end, let's quickly revise the phase estimation algorithm. In the phase estimation algorithm, our inputs are a unitary matrix U and eigenvector of that unitary matrix, say ket V. Our output is phase theta such that unitary matrix times eigenvector is equals to eigenvalue, which is Euler constant raised to power 2 pi I theta times eigenvector. So by calculating theta, we can basically find eigenvalue of unitary matrix U corresponding to eigenvector ket V. Now to realize order finding, the basic idea is that we will prepare a special unitary matrix. Let's call the unitary matrix M alpha. Now that special unitary matrix that we will prepare for the order finding algorithm, its eigenvalues has order R in it. So we will give that unitary matrix and eigenvectors of that unitary matrix as input to our phase estimation. The phase estimation will provide us the order R on our output. So let me clear the board first, and then we will discuss this unitary matrix, list its eigenvector and eigenvalues, and see how can we proceed further. We define our special unitary matrix to find order R as M alpha. Now M alpha takes input of ket X, where X belongs to our multiplicative group over modulus n, and the output of this unitary operation is that our input is multiplied by alpha, and we also have to calculate our mod n here. So that's our output. You can ask that how come this is a unitary matrix? This is a unitary matrix because it represents a reversible operation. We can always find a matrix M alpha inverse because alpha belongs to multiplicative group. So in the multiplicative group we can find inverse of every element, and when we multiply our matrix M alpha inverse with M alpha, our answer will be equals to identity. So this is a reversible operation. You can also ask that we say that X takes these values. What about the other values? This unitary matrix is not defined for other values? Yes, this unitary matrix is defined for the other values. In those cases, our input and output remains the same. For only when the X is member of this multiplicative group, then this unitary matrix behave like this. Otherwise, input and output remains the same. So now let's write eigenvectors and eigenvalues for M. We first write eigenvectors for my special operation M. Eigenvectors of M are rho 0, rho 1, rho 2, dot dot dot, and the last eigenvector is rho r minus 1, where rho j is defined as rho j is defined as 1 over square root of r summation I equals to 0 to r minus 1 omega r raised to power minus I times j and ket alpha raised to power I. So this is the definition of my eigenvector. I can expand this definition for clarity. So now let's write my rho j in expanded form. It will be equals to 1 over square root of r. The first term according to their summation will be ket 1. The second term will be omega r raised to power minus j times alpha, ket alpha. Next term will be omega r raised to power minus 2j times alpha square. And the last term of my eigenvector rho j will be omega r raised to power minus r minus 1 j times alpha r minus 1. So that's my eigenvector rho j in expanded form. Similarly, I can write my eigenvalues for my special matrix M corresponding to eigenvector rho 0. My eigenvalue will be omega r raised to power 0, which is equals to 1. Corresponding to eigenvector rho 1, my eigenvalue will be omega r raised to power 1, which is basically omega r. Corresponding to rho 2, my eigenvalue will be omega r raised to power 2. And similarly, my eigenvalue corresponding to the last eigenvector rho r minus 1 will be omega r raised to power r minus 1. So this is my eigenvector and this is corresponding eigenvalue. Now you should ask that how we are sure that these are the eigenvector and eigenvalues of this matrix. We can verify that these are indeed valid eigenvalues and eigenvector by using the definitions of eigenvector and eigenvalue, because when we multiply an eigenvector by its matrix, our answer is eigenvalue times that eigenvector. So we can use that equation to verify them. So if these are valid eigenvector and eigenvalues, then this equation must be upheld. That my unitary matrix M times eigenvector rho j must be equals to eigenvalue omega r raised to power j times eigenvector rho j. So I start from the left hand side, I expand left hand side in order to reach my right hand side. So let's start from the left hand side. Now when I apply my unitary matrix M on rho j, then each entry of vector rho j is multiplied by alpha. So this is my rho j here. The first entry would multiply by alpha, this will multiply by alpha, so this will become alpha, this will become alpha square, this will become alpha cube, and so on. So I will get 1 over square root of r times alpha plus omega r raised to power minus j times alpha square plus omega r raised to power minus 2j times alpha cube plus, and the last entry of my eigenvector will become omega r raised to power minus r minus 1j times alpha raised to power r. So this is my transform rho j after the application of this unitary operation. Now I take out common omega r raised to power j from this. When I take out common omega r raised to power j from here, then as I take out this, then all the entries inside will be multiplied by omega r raised to power minus j, because I have taken out this common, so I have to multiply all entries by omega r raised to power minus j. So this will multiply by omega r raised to power minus j, and this is the correct entry of rho j. So I am now retrieving rho j inside. This is correct. This will be multiplied by omega r raised to power minus j. So this will become minus 2j here, and this is correct entry of rho j. See this, and this will multiply by omega r raised to power minus j will become 3j, and this is also correct because here I have my I is equals to 3 and here my I is equals to 3. Now what will happen with the last entry? When it multiplies by omega r raised to power minus j, then it will become omega r and raised to power minus rj. This is the periodic function omega r, we know from the Fourier transformation, and when we take the mode of r, then it will become 0. So omega r raised to power r is omega r raised to power r mod r, and which is basically equals to omega r raised to power 0. So this will become omega r raised to power 0, and this will become 1. So here I will have 1, and we know that by definition of our order finding algorithm that alpha raised to power r is equals to 1. Remember, we have written it somewhere here, so we can replace this by 1, and this last entry is basically the first entry of my rho j. So I have now inside here the whole rho j, and I have taken out omega r. So this thing is now equal to my right hand side. Hence I have proved that these are indeed correct eigenvectors and eigenvalues of this unitary operation. Now, how we can use those eigenvectors and eigenvalues to find our period? To explain that idea, I have to first clear my board. So let me clear the board to write that main idea. So I clear my board from here. To my phase estimation algorithm, I can give input of my special matrix, unitary matrix M alpha, and its eigenvector rho 1. And what will be my output? My output will be theta corresponding to this eigenvector. I know that the eigenvalue of this eigenvector is omega r raised to power 1. So I don't have to write 1 here. It's omega r. Omega r definition is Euler constant raised to power 2 pi I over r. So in this case, my theta will be 1 over r, because my theta is here 1 over r. So I will get my output of 1 over r. And now what I can do is take the reciprocal of this output and get my r. Yahoo! However, there is one problem. I cannot prepare rho 1 without knowing r beforehand. And if I cannot prepare rho 1, I can't use it. So we are stuck once again. The solution of our problem is that instead of giving a specific eigenvector rho 1 here as input to our algorithm, we give it superposition of all the eigenvectors as input. So instead of giving rho 1, we give it input rho 0 plus rho 1 plus dot 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 plus rho r minus 1 divided by square root of r. So this is the equal superposition of all the eigenvectors. So you will ask that if we can create equal superposition of all the eigenvectors, we still have to know r beforehand. We still have to know the order beforehand. But no, we don't have to know the order beforehand, because the equal superposition of all these eigenvectors is equal to ket 1. So we will be in fact giving input of ket 1. To create ket 1, we don't have to know the order beforehand. So we can show easily that these all vectors, when summed together and divided by square root of r, to create equal superposition, then they become equals to ket 1. So what will be our output? Our output could be a theta of any of those vectors with equal probability. What could be theta of a random vector rho j? So we know that a vector rho j has eigenvalue of omega r raised to power j, and we know that this is equals to Euler constant raised to power 2 pi I j over r. So this thing is our theta. So in this case, I will get answer of j over r instead of, and I don't know the value of j. J is uniformly distributed from 0 to r minus 1. J is uniformly distributed from 0 to r minus 1. So how we can retrieve our r? We will perform two steps. Number one, we will use continuous fraction to write theta in fractions. So there is something known as continued fraction. We will use continued fractions algorithm to convert theta into fractions of j over r, but it's possible that our denominator and numerator are not in the smallest possible terms. So we might not have the exact value. So what we will do in the step 2 is that we will rerun this algorithm. We will rerun this algorithm multiple times and we will get different values of denominator and numerator. Let's say maybe j1 and r1. Next time we will get theta equals to j2 and r2. This is in the denominator we must have r, but because we are not getting the exact value, so it's possible that we have some non-exact values like j2 and r2 and so on. At the end we will take LCM of all the denominator values like r1, r2 and so on, and this will gives us our r with very high probability. So that's it for this video. In the next video, let's do an example to make our concepts more clear.